You update a Kubernetes object. The API server says the update succeeded. Then one line later, you read it again and get the old value. Maybe the deployment still says 3 replicas, even though you just changed it to 5. Nothing crashed, the update was not rolled back. The controller can still be working exactly as designed. Your write and your next read may travel through 2 different paths. The write goes to the API server. With the default controller-runtime manager client, the read normally comes from a local cache. That cache catches up asynchronously, so a healthy controller can briefly read the past. Let us see why when it becomes dangerous and how you keep the controller correct. One client object in your reconciler looks like one direct API connection. You call r.get for the latest object. You call r.update to store a change. Then another r.get should confirm it, right? That is the naive model. The manager-provided client is normally a split client. Get and list operations for cached object types read from local memory. Create, update, patch, and delete operations go directly to the API server. There are configurable exceptions, but this split is the default idea you should carry into a controller review. A successful write does not synchronously invalidate the local cache. The controller runtime documentation does not promise sequential create then get or update then get coherence. So how does the cache get its data? Conceptually, the manager establishes an initial view of the objects it needs. Then it follows later changes through a watch stream. An informer maintains a local store. The API server sends additions, modifications, and deletions. Resource version information lets the client continue from a known point and recover after a broken watch. Your reconciler receives an object name and namespace. r.get can look up that key locally instead of sending another network request. Controllers under one manager can share this cache infrastructure. Reconciles reuse the local view instead of repeatedly asking the API server for the same state. But the informer documentation uses a very specific phrase, eventually consistent. The store converges toward authoritative state. It is not a synchronized mirror of every write your code just made. Let us slow the failure down. Suppose the cache currently holds a deployment at resource version 41 with 3 replicas. Your reconciler sets replicas to 5. Then it calls update. The API server accepts the write and stores a newer object resource version 42. The update call returns successfully. But the cache still has version 41. It has not processed the watch event for version 42 yet. If you immediately call r.get, the read can return 3 replicas. The watch event arrives, the informer updates its store, and a later read sees 5. The delay is not a contract, it may be brief or longer during communication and processing trouble. Your correctness cannot depend on a guest sleep. On purpose does not mean the framework maliciously returns old data. It chooses an asynchronous cached read architecture, and possible staleness is the cost. This sounds unsafe only if we design reconciliation like a one-time command handler. Kubernetes reconciliation is level-based. An event usually puts a name and namespace into a work queue. The reconciler compares observed state with desired state, then moves the system closer. It may run again. Duplicate requests can merge. What matters is convergence, not replaying every event as a unique instruction. That is why idempotency is essential. Give child object deterministic identities and make repeated create or update attempts safe. For external services, use an idempotency key or durable state to avoid acting twice. If the cache is old, another reconcile should do nothing harmful or safely repeat the intent. The stale read is not your correctness mechanism. Repeated convergence is. Here are the practical rules. First, do not write an object and immediately read the cache just to prove it worked. Use the write result when possible. Otherwise, return and let a watch event or deliberate requeue drive the next observation. Second, handle conflicts instead of hiding them. If another writer changed the object after your cached read, an update with the old resource version can receive a 409 conflict. That prevents a silent lost update, reread, recompute, and retry appropriately. Third, do not call a random sleep consistency. It can be too short during trouble and needless during normal operation. Finally, keep side effects retry safe. A database call, cloud request, or child resource creation must tolerate repeated reconciliation. Sometimes cache state genuinely does not fit the decision you are making. The manager exposes get APIReader, which reads directly from the API server. Its documentation says to use it sparingly. A direct read has network and control plane cost. If every reconcile bypasses the cache, you remove much of the reason it exists. Use a direct reader for a narrow freshness sensitive check, not as a reflex after every write. Disable for can root selected object types to live lookups that may suit a type you read rarely and do not want to retain locally. It is not a global cure for stale data. A live Kubernetes read still does not make the controller, the Kubernetes API server, and an external cloud API one atomic transaction. There is one more cache behavior worth knowing. By default, a get or list for a structured type without an informer can start a new informer. That can add a watch and retain objects you did not expect. In a large cluster, an innocent-looking list can change memory and watch footprint. Reader fail on missing informer returns an error instead of silently creating that informer. You can also narrow the cache by namespace, object type label or field selector. If managed fields are unnecessary, a documented transform can strip them before catching. One more trap. Sync period is not a periodic API refresh, it triggers local synthetic update events. It does not make stale data fresh. Cache design is controller design, decide what you watch, retain and read directly. The default Kubernetes controller client separates cheap cached reads from direct writes, so read after write freshness is not guaranteed. Your controller stays correct by reconciling desired state repeatedly, making side effects idempotent, and treating conflicts as normal concurrency control. Use direct reads and cache bypasses only where freshness or cache cost genuinely demands them. Once you see the split path, stale reads, stop looking random and start looking like an architectural trade-off CTA. If this helped you debug the controller mental model, share it with someone building Kubernetes operators and subscribe for more engineering